All right. I think we're rolling. So, had a little bit of a mishap. I did about an hour and a half lecture, and then at the end, the active presenter crashed. So, I wasn't happy about that. I didn't find a way to recover it. So, I called my office mate, told him I wasn't coming into work, banged on my drum set for, I don't know, an hour or so, and felt better. So, now here we are. Okay. I learned a couple things in the last lecture, and one of them was that I spent the entire hour and a half talking about the homework solutions. Okay? So, in the past, I have uh, not dedicated any lecture time to talking about the homework solutions, really. Kind of the what I thought in my mind was happening is students were doing the homework, and they were then going and doing the looking at the homework solutions after I grade them and understanding what they did wrong and so on and so forth. And they were just coming to me, or weren't coming to me with questions because they understood everything that was in the homework. And then we get to the exam, and it was very evident that they didn't understand everything. And some of the feedback I get from the teacher evaluations is that I don't go over the homework, and so they feel students feel a little lost. So well, this whole, record everything and put it online has now encouraged me to go ahead and go through the solutions and dedicate some time, go through the solutions, and students that understand the homework don't have to go through it. But for students that I don't know if I said that right, students that do understand the homework don't have to go through the solutions review, but students who are struggling with the homework, which would be just about every one of you, uh, should probably listen to the homework review. So, my intention today, of course, was to do the a single lecture, but now, because of unforeseen events, I decided to go ahead and re-record what I had said last time that got erased, and do basically a solutions review, and then I'll do an additional separate lecture today, hopefully covering all the stuff that I had intended to cover this morning. So anyway, trying to make lemonade out of lemons. I was not very happy, and I still cannot figure out a good way to get this active presenter to continually be backing up what I'm what I'm doing. It's authoring it into it's writing it into a file, but that file is not accessible. And when the software crashes, I'm not figuring out a way to access those files. But anyway, I'm going to be really mad if the software crashes again. Okay, so we're gonna use this time to go through the solutions, and then, like I say, I'll try to hammer out another lecture here shortly. Got the whole day dedicated to you all. That's what I decided to do. Is I was already behind with the class, so I'm just gonna stay home from work and get caught up. And interestingly enough, it's snowing outside, so it's a really nice day to just stay home and enjoy the snow. All right, so I'm going to try to go through this maybe a little quicker than I did the last time. I got erased because that was an hour and a half. I'd like to trim this down to maybe an hour, if at all possible. I did go over some tidbits of information in addition to the lecture, so things trying to help you understand things in addition to the lecture. So I may still put those in there. All right, so number one, a number of folks were able to get this one. A couple of things to remember is that CPI literally stands for clock cycles per instruction. That is the units for CPI. Okay, and for all these problems, I want you to use the units because the units tell you how you should arrange things in the equations. See, we're not physicists here where we've got these weird constants that we have to factor in and all of that. So our equations are very simple, and if you look at the units, you can understand how to arrange things. So I'll talk about that in a second. So clock cycles per instruction, and what we're trying to do is find the average clock cycles per instruction for a given instruction stream. Okay, and so what we say is that the CPI for a MIPS machine is 1.3 for loads and stores. Okay, so we're going to calculate a weighted average, and So for loads and stores, these are our loads and stores. We want to add that percentage up and multiply it by 1.3. Okay. And then 1.2 for control flow. These are our control flow instructions. So we want to add these percentages up, multiply that by 1.2. Okay. And then finally 1.1 for ALU instructions. These are our ALU instructions. We want to go ahead and add those percentages up and multiply them by 1.1. And then we add all that together, and that gives us our average CPI. Okay. And so we can see in the solutions that's precisely what I've done here. Okay, so here I add up all the percentages. There they are, and then I put them into our weighted average equation. Okay, um, so that's really all there is to part A. Okay, part B is giving us the clock rate, and of course we have the number of dynamic instructions, the instruction count up here. And with that and our newly calculated CPI, which is clock cycles per instruction, then we want to go ahead and calculate the execution time of a program. So again, this is where units come in to help us, is we're looking for seconds. That's what we're trying to solve, okay? And we have CPI, which is clock cycles per instruction. When we multiply that by the dynamic instruction count, which is just instructions, okay, we get the amount of clock cycles that it takes to execute our program. So clock cycles per instruction times instructions, okay, gives us cycles. And then if we divide that by cycles per second, which in this case 2.5 gigahertz is 2.5 billion cycles per second, okay, then we can see all these different things cancel out, and in the end we end up with seconds. Okay, so that's really all there is to it. Okay, part B just really asks you to redo A and B with some different numbers, different clock rate, different weighted CPI average to calculate. Okay, and in the end you're going to get time, and then it asks for speed up. Okay. A common mistake that students are making is oftentimes I will give you a problem and I ask for speed up and there's actually a slowdown, and so you'll say, well, there is no speed up, and then you won't calculate speed up. Okay, that isn't the case for this problem. There actually is a speed up, but in the case where I ask for the speed up, I want you to calculate the speed up, and if you get a fractional component, fine. That indicates that that there was no speed up. There was actually a slowdown. But I want you to go through the exercise of calculating it. Okay, just trying to point out common mistakes I've seen as I went through these homeworks. So by the way, the graded homeworks that are posted on the Learn system, and so if you have any questions about your grade or whatever, please feel free to email me. If you have any concerns about how to do a particular problem, actually what I'd really like you to do is post on the discussion board, because other students probably have that same question and it can benefit them. So far, nobody's used my discussion board, so I don't know. Anyway, nobody likes discussion boards, I guess. All right, so that's really all there is for that problem. Okay, number 2, for each of the problems, I want you to show the opcode, RS, RT, and the immediate field. Okay, so, all right, so most people mostly got this problem. Some people just simply said, oh, well, you know, for this problem, T5 is RS, T6 is RT, and T4 is RD, and then you just left it at that. If you'll notice in my solutions, I provide the base 10 value for each of those, and that's really what I was looking for. Or some folks even went a step further and gave the base 2 representation of those, and either of those were correct. But I probably marked off points if all you did was give me T5, T6. You only did half of the problem. So, okay, you were able to identify which one of these is RS, which one's RT, which one's RD, but then you didn't do the rest of the decoding, which require. In fact, I think the problem even, I don't know if did the problem even mention about 2.4? Oh, no, it doesn't, but whatever. We use figure 2.4 in the book to translate the mnemonic register mnemonic to an actual number. Okay, we want to convert it to something that that the machine um, understand. So I probably should clarify that problem in the future. Just real quickly, I want to talk about bases. Here we have numbers that are either base 2 or base 10. So I usually incorporate a little suffix here, like this suffix, or not suffix, subscript. This subscript is 10, which means this is a base 10 number, and then like this one is 2, so it means it's a base 2 number. Hexadecimal, a lot of times I'll do a 0x and then the number, in lieu of doing a subscript 16, but you know, if we have something like this, it's pretty evident it's hexadecimal. But if we have something like this could be in hexadecimal, and so we should either indicate it like that or with a 0x. Okay, all right. All right, so most people got that one. Pretty straightforward. Look at my homework solutions. See if they make sense. Um, Okay, most people got problem 3 correct and problem 4 correct, so that was good. I don't recall any real mistakes that stood out here. Okay, okay, for problem 5, you know, a lot of people miss this one, but really what I'm looking for is Louis. Okay, I'm looking for Louis. Louis is the best way to actually, really the only way to do this is with a load upper immediate instruction. Okay, I got lost. Let's see. Oh, 5. Okay, one more. Okay. Okay, so here's the solution. The pseudo instruction you would use, which I didn't expect a lot of people to get this, because you really understand this if you spent a lot of time programming in MIPS assembly, which hopefully not a lot of you are having to do. So LA is load address, um, and that's what it stands for. And it breaks up into a load upper immediate and an ORI. Okay. Now there are actually mistakes in the homework solutions that I didn't find out till I went through and graded. What happens? I grade your homework, and then that causes me to find mistakes in my own homework solutions. So I plan to upload probably tomorrow the revised homework solutions. Um, and so one of the mistakes I made is I don't know where T0 came from. This should be T1. Okay. So what load upper immediate does is it takes this immediate value. Whoops, didn't mean to cross it out. This immediate value and it puts it into the upper 16 bits of T1. Okay. And then the ORI takes the lower 16 bits of our address here, okay, and it puts it into an immediate value, and then it simply ORs T1, okay. So some people didn't use ORI but used like add-I, for example. And for this particular example, that would work, but that's not the correct answer. And the reason is because add-I sign extends, and of course add-I unsigned for whatever reason also sign extends. So neither of those are good options. OR-I is really what we're looking for. Okay. Let me just show you a quick example. So Louis, after Louis executes, we're going to have the following value in T1. Okay. 0, 1, and then Louis puts zeros in the lower 16 bits, okay? And if you're doing an add-I, what you're going to do is you're going to add, and so you're going to add this value, 4924, and in this particular case, the upper bit of this most significant nibble of your 16-bit immediate is 0, so it's going to 0 extend. So for this particular example, that works just fine. But let's pretend this this 4 was an F, for example. Okay, so the F now is the most significant bit is in fact 1. Okay, So let's see, 5, 9. Okay, well, what's going to happen is the add or add I, either one of those, is going to then sign extend this. Okay, it's going to basically do this number. Okay, that's not what we want to do. Okay, so that'll compute the wrong value. Okay, so let's see. I don't trust this darn active presenter, so I'm going to double check that it's doing what I want it to. It looks like it is recording. Hopefully it does. Okay, I paused the video just a little bit to make sure that we're still recording. I don't trust this tool, so probably every 15 minutes or so I'm going to double check it. Okay, all right. So I explained why add I does not work, and okay. So the next part of that problem asks you if the current PC value is all zeros, can you jump to this location to the address here in a single jump? And most people got B and C correct, but then a number of people got D incorrect. So the answer to B, C, and D is all no. And the reason is because if you recall from lab and lecture of how the jump address is actually created, is it's created by stealing the upper 4 bits of the PC and combining that with the 28-bit jump address, okay, that you get from the 26-bit portion of the instruction that's then left shifted by 2. So you take the 26 bits, lower 26 bits of your instruction, you left shift that by 2, and then you concatenate that with uh, the upper 4 bits of actually not just PC, but PC plus 4. Okay, so what that really means is if we take PC, which is in this case for D is 0x 1 F F F. There's another F there. F 0 0 0. Add 4 to that. Okay, so we add 4, and we get 4 0 0 F F F 1 F 1. Okay, and then examine the upper 4 bits. Well, the upper 4 bits is this first nibble, which is 1. So that's in binary. That's 0 0 1. Okay, so there's my base 2, by the way, indicating that it's base 2. And this is base 2, which there's my base subscript 2, indicating this is base 2. And we see that these two are not equal. This is not equal to this, so that means we cannot jump to it. Okay, it's really that simple. Uh, and it all has to do with how our jump addresses are actually created. Okay, um, so uh, okay, I lost my train of thought here. Okay, so uh, all right, so again, the answer to D is also no. Now, in the past, I've given a problem where these upper 4 bits, or not the upper, but the lower nibbles were this. Okay, let's see, 2, 3, 4, 5, 6, and then we could put an E here. Okay, so when we add this, okay, uh, this is going to roll over. Okay, so let's see what that value is. Okay. Okay, E is 13. Okay, no, it's 14 in hexadecimal. Okay, 14. We add 4 to it, we get uh, 18. So then we end up with this. We end up with 2, and then a carry. And this carry ripples all the way through. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then this will be a 2. So in the past, I've given a problem similar to this, and actually, this may make for a good exam question as well. Just to modify things a little bit, because on the exam, I take your homework problems and I modify them a bit, and so then in that case, this 2 matches this 2 here, so then we can actually jump to that address. Okay. Okay. Yeah, forgot to mention a little bit about the exam. See, I'm going to end up leaving things out because I already recorded this lecture, and I'm not going to remember what I actually said in which lecture. Um, but the exam is I'm gonna give it out here this week sometime. I was thinking maybe like Thursday time frame, and then make it due Tuesday. So normally, I mean, we have the exam almost right after we've covered all the material that we're going to cover for that exam, but this COVID-19 thing has thrown everybody for a loop. And so in this case, your exam's going to cover everything that we've covered in homeworks 1 and 2, and then wherever at some point the lecture's left off there. The exam, remember, is going to be open note, open lecture, everything but open friend. Don't discuss the exam with colleagues and whatnot. And so if something, uh, I don't have to worry too much about putting things on the exam. If something I put on the exam uh, is covered later in a lecture, you can just go find it in the lecture. So anyway, all right. So let's see. Part E is if you cannot use a single um, jump instruction to get to the address above, how would you go about jumping to that address? So very few people got this correct, but what I'm looking for is um, using uh, part A, okay, in conjunction with a jump register. Okay, so if you use part A to go ahead and put the address into a register, and then you use a jump register to then jump to that, that's how you can get to that address. Now, notice here I've used the AT register, which is special for the assembler. So, because this is actually something the assembler will do. If you jump to a label and then that label ends up getting put very far away from wherever it places the code, when it goes and stitches everything up during the linking phase, it will replace that single jump with these 2 instructions. Which, well, these 3 instructions really. Okay. Okay. I think that's all we really need to say for problem 5. Okay. Let's see. Okay. Problem 6. Decent amount of people got this right. Not fully. I don't know that anybody fully got it correct, but let's just go through real quickly how to do this. My homework solutions I actually just annotated on top of the homework problem to show you how to do this. So let's just go through this real quickly. So I really like this problem because it's forcing you to think about the cost of components and everything in terms of time, and it teaches you how to calculate the critical path. Okay, so we start here on with the PC. That's where everything's going to start. Okay, and we go through the instruction memory, which takes 200 picoseconds. So then we see here, I go ahead and I like to write the arrival times of each of these signals. So here we have 200 picoseconds, 200 picoseconds to arrive here, right? So then the register read takes another 90, so that puts us arriving at the A input of the ALU at 290. Okay. Also, the input of this mux in front of for the B input of the ALU at 290. Okay. There's 2 inputs to this mux, so the second input actually goes through the sign extension unit, which is 15 picoseconds. So we end up arriving here at 215. I didn't even write it down because I knew that 290 was the bigger one. Okay, so we take the greater of the two. Each of these, when we have multiple arrivals of signals, okay, we take the maximum, the greatest of all of them. Okay, so that means we're gonna be 290 here. So then we'll arrive at the B side of the ALU after 15 picoseconds later, which is the time to get through a mux. And so we end up with 305. 305 is greater than 290, so that is the time of arrival of our data into our ALU. Our ALU takes an additional 100 picoseconds, so we add on the 305, we go ahead and add 100, and we get 405. Okay. Now we have another path here going into the memory, and that's a bypass path that comes from our register file, which has the same arrival time over here, which is 290. Well, of course, 405 is much larger than 290, so that's going to be our critical path. And then the data memory requires 200 picoseconds, so then we'll arrive at this last mux here at 605 picoseconds. Okay. We also have this path, the ALU path that goes around, so the other input to our mux arrives at 405. 605 is clearly larger than 405, so that's going to be our critical path. And then we come back around here, and it requires another. So after the mux delay, which is 15 picoseconds, we end up at 620. So we arrive here at the input of our register file at 620. Now, the register file requires 40 picoseconds to write, so 620 plus 40 is 660. Okay, so that is our critical path. That's also the answer to B here. B asks what's the latency of the load instruction, this data path. Well, the load instruction happens to be the longest running instruction, so it sets the critical path. Okay, and that's because it uses all of the pieces of our data path. Okay, so for part A, it asks for the clock rate, which is 1 over the basically the critical path. And so 1 over 660 picoseconds gives us 1.51 gigahertz. Okay. All right. These problems, I mean, it depends on, all of these delays depend on what target technology you're using, and I kind of just made these numbers up and tried to make them all sort of correct relative to each other, and but depending on uh, what target technology you're implementing this in, you'll have different delay times. Um, do I honestly think you can get a single cycle design to run at 1.5 gigahertz? Maybe super simple in a modern process technology, but again, this is a little unrealistic. Okay. Okay. All right. Now, C and D. What I did with C and D, there's a couple of ways to properly answer C and D. One, you could do like I did in the example, and that's trace through and figure out. It's like, oh well, for the store instruction, you know that you're basically done at the end of the memory. You don't actually have to go through this mux and then back into the register file. So for C, then you actually end up with 605 picoseconds. Um, and with the ALU, well, you're not using the data memory, so you could say, well, it's 405 then plus the delay through the mux and the time to write into the register file. That would be a correct answer. Um, but also, some people just put for C and D, they put 660 picoseconds, and that's also correct. The reason that's also correct is because honestly, this is going to be clocked, so you're going to clock it, and it doesn't matter how quickly the data flows through your data path. You're only going to complete the instruction at the end of the clock cycle. Okay, so that's 660 picoseconds. So I'll take either of those answers. If for whatever reason I marked you wrong, email me or whatever. So like I say, either of those are good answers to these problems. Okay, part E, a lot of people thought just way too much about it. Okay, like a lot of people, it was interesting. A lot of people did a number of calculations and somehow arrived at 1 clock cycle per instruction. But really, intuition should tell you what the answer to this is. It's not a trick question. It says consider this single cycle data path. Okay, single cycle. Every instruction completes in a cycle. So, what is our clock cycles per instruction for this particular data path? It's 1. It's 1 clock cycle per instruction. Okay. All right. The next part of this problem asks us to look at the pipeline data path, okay, which is shown on the next page. And so basically what we do with the pipeline data path is we start out by ignoring flip-flop delays, and so we just calculate the delay through each of the paths for each of the stages, okay? And with that I arrive at the following, okay? The instruction fetch is 200 picoseconds, decode is 90 picoseconds, execute is 115, memory is 200, and write back is 55 picoseconds, okay? And then you basically take the maximum of all of these times, okay? Because each stage has to take the exact same amount of time. Each stage takes a clock cycle. So we're trying to figure out what is the maximum clock cycle, clock rate we can set this to. Stated in another way, what is the maximum cycle time necessary to make this work? So our largest stages are the fetch and memory stages, and they take 200 picoseconds. So that means that our minimum cycle time that we can have for this design is 200 picoseconds. We can't try to make that cycle time smaller because then we won't meet timing. Okay, we'll have data arriving during the setup and hold time, or even after the setup and hold time. Okay, so so for G, well, let's see. Oh, so let's go back to F. So F says, what's the maximum achievable clock rate? Well, it's just simply 1 over our critical path, which is 200 picoseconds, okay, which is 5 gigahertz. Okay? All right. Part G says, what is the latency of the load instruction? Well, the load instruction takes 5 cycles to complete. Okay, it has to go all the way through the pipeline. Okay, 5 cycles to complete. And so 5 times 200 picoseconds is 1,000 picoseconds, or 1 nanosecond. Okay? For H, what is the latency of the ALU? Well, ALU instructions have to go through the entire pipeline, and a lot of folks got this right. And so its delay is also 1,000 picoseconds. Okay, so what you're going to find is now every instruction has to go through the entire pipeline, and so every instruction now has a latency um, of 1,000 picoseconds. And the reason I really like this problem is because it shows you that you actually, by pipeline, you're actually increasing the latency. Okay, if you recall, a load instruction could complete in 660 picoseconds with the single cycle design, but now with the pipeline design, it takes 1,000 picoseconds. Okay, but what we're improving, of course, when we're pipelining is instruction throughput. Okay, the instructions, ideally what we're trying to achieve without data hazards is the throughput of 1 cycle per instruction, which is what we achieve with the single cycle. But with the pipeline design, our clock rate should be significantly higher. And in this toy example, we see that it is. Okay? All right, let's see. Okay, so part I actually asks us to figure out what the speed up is, and we're assuming no pipeline hazards, uh, and you're basing throughput purely on the clock rate. Okay, so you're assuming both achieve a CPI of 1 cycle per instruction, and so with that, it's just a ratio of the clock rate, which happens to be 3.3. Okay. Now part J says, well, let's hold on there. There's a cost to pipelining, and that's that we have this flip-flop delay. So go ahead and add 20 picoseconds for flip-flop delay. So what you end up with is, instead of 200 picosecond critical path, you end up with 220 picosecond critical path. You calculate the clock rate from that, and you end up with 4.5 gigahertz. Okay. Now, if you wanted to calculate the speed up now over the single cycle design, considering flip-flop delay, you'll find that it drops down to 3x. Okay, which makes sense because 660 picoseconds divided by 220 picoseconds is 3. So we end up with a 3x improvement in clock rate after considering flip-flop delay. Okay, K says, why is the single cycle design impractical? Well, it leaves a lot of components idle while going through the clock cycle. Your latency, your critical path is very long. All of these are good answers. Okay. Okay. And part L basically says, all right, compare the speed up you you calculated in 6i with that of the ideal speed up, okay, of a 5-stage pipeline, and then what are some things that can reduce the speed up of pipelining? So we talked about this in lecture. The ideal speed up, of course, is for this particular design is 5x, but we're seeing that when we include flip-flop delay, we end up with 3x. If we don't include that, we end up with 3.3x. Okay, and that's quite a ways off from 5x. So what are the things that are leading to inefficiencies here? Well, it's that internal fragmentation. Okay, if we go back and look up here, we have the decode, the execute, which the execute's where most of the actual work goes on inside the pipeline, and the write back are all much less than the 200 picoseconds required for the fetch and memory stage. Okay, so there's a lot of inefficiency here. That's internal fragmentation. And then also, the flip flop delay now becomes much more significant. Okay, and with the smaller cycle time, so flip flop delay. Other correct answers to this problem is a lot of you mentioned data hazards, and that's perfect. And it don't just stop at data hazards, also control hazards and structural hazards. All of those things erode away from our ideal speed up. Okay, moving along. Let's see. Okay, problem 7. Okay, a number of you did get this correct. Um, although I am surprised at how many times I've done this. I've drawn these little circles and arrows. I've done this a number of times, and some folks were still confused as to what I'm asking for when I say identify the data dependencies in the code. This is exactly what I'm looking for. Okay, this simple notation indicates that there's a data dependency between the add and the load word with this T1 register. Okay. Now, a number of folks would get the data dependency that's immediately following, but then some would forget about these other ones. See, so there's actually, and then very few people remembered this data dependency and this one. Okay, so we have all these data dependencies, and then we have these ones. Okay, whoops, I don't know where that's going. That's going here. This one, so on and so forth. You get the point, right? And then T6 is over here, so on and so forth. Okay, that's what I'm looking for part A. Okay, and you'll see that in my solutions. Okay, part B, we assume that it's a 5-stage pipeline without data forwarding or interlocking. Okay, so what that means is that we have to insert a number of no-ops, and some of you inserted only one no-op, some of you inserted 3 no-ops. Really what we're looking for is 2, and the reason is because we also have this little tidbit that we add, which is assume that register write happens in the beginning of the clock cycle and read happens at the end. Okay, so we need a diagram to really see how this works. Okay, so let's look at this data dependency right here. Okay, we have an add, and then immediately following we have a load word. Okay, so the add, okay, is going to go through the pipeline, IF, ID, EX, mem, write back. Okay, and the load word, if we don't stall, is going to be IF, ID, EX, EX, mem, write back. Okay, and what we're going to do is we're going to attempt to forward from the write back, because the add actually writes into the write back. Okay, we would have to forward all the way to the decode. Okay, well, there is no forwarding, so we can't do that. But we have to line these up. Okay, if there's no forwarding, we have to line these up. So we have to scoot this guy over. Okay, so we can do that by adding no ops. Okay, so let's add some no ops here. No op, and I'm only going to add 2. Okay, some people added 3, and I'll show you why we can get by with only 2. So IF, ID, EX, mem, IF, ID, EX. Of course, the mem goes off the page. Okay, and then here's this load word. So I'm saying that we can actually do this with only 2 no-ops. I'll show you why. Okay. All right, so what we have now is we actually have the add, the consumer's write back, lined up with the load word, the producer's decode stage. Okay. Now, because of this little tidbit at the end here where I say also assume that register write happens in the beginning of the clock cycle and read happens at the end, that means that what's going to happen is the add is going to write its result into the register file at the beginning, the first half of this cycle. Let's go ahead and label it 1, 2, 3, 4, 5. This is cycle 5. And then at the end of cycle 5, the latter half, okay, the load word will then read. And so what we have is a internal bypassing going on inside the register file. Now, if we didn't have this, okay, then you would be correct in needing 3 cycles, okay? So if that doesn't make sense, do message me, post something to the discussion board, whatever. So we're gonna need 2 cycles here, 2 no-ops here, okay. And then some people inserted 2 no-ops here, but we actually only need 1 no-op here, and I'll tell you why. Between this this load word and the XOR, is look at the data dependency. Okay, we have the load word, T5 here, and then T6 actually isn't used by this XOR, but it's actually used by this XOR. Okay, so that means between the second load word and the first XOR, we need 2 instructions, okay, with no dependencies, and so the load word, the third load word, actually gives us one of those instruction gap spaces. Okay. So then we only need a second no-op there. And then now, unfortunately, the XORs, the 2 XORs, okay, they have, they're back to back. So we have to insert 2 no-ops here, okay? And then the same goes for this store word, okay? And then there's no data dependency here between the store word and the add I, okay? All right, now, the next part, if you reorder the code, okay, to eliminate as many no-ops. Okay, well, so then, okay, part C then says, okay, now we allow full data forwarding. And it turns out I went and modified this problem without, I guess, thinking through too much of the modification. But when I modified the problem, I basically did so in such a way where we don't actually need any no-ops, okay? Because when we allow full data forwarding, the only time we need a no-op, okay, is when we have a load word, okay, that's producing a value and then an ALU operation that immediately follows that and is consuming it, okay? But in this case, because we have this load word here, this is where our no-op might have been if we didn't have this load word, okay? Now, of course, I can get tricky, and I might do this on the exam, is if we were to interchange these two, okay? So if we interchange these 2 load words, then we would actually need a no-op here, because we would have this instruction immediately preceding the XOR. Okay, and so I could very easily modify this problem, and I might do that for the exam. Is just go ahead and I could flip these, and then you would have to put a no-op, and then part D, which in this example, because there are no no-ops, you don't really do anything to reorder the code. But if I had interchanged these 2 load words, then you would just simply swap the load words, and you could get rid of the no-op. Okay. Okay. All right. Problem 8. Yeah, that was a fun one. Okay. Most people got some of this right, okay, but most everyone got all of it wrong. I don't think anybody got it 100% right. So what I want you to do is I want you to draw the execution diagram. And we were drawing execution diagrams for quite a bit in lecture, okay? And I'll show you what that looks like. This is what I was looking for. Okay, so we have the cycle time up here. We've got the program here, and it goes down this way. And then we indicate what state we're in. And I chose to do a really abbreviated notation, which is fetch, decode, execute, mem, and write back, and that's perfectly acceptable. Fits nicely in these little square boxes. Okay. Now some of you are confused on how the program is supposed to flow, and that's possibly because you did not read the comments. Okay. So if you read the comments, I'm saying, okay, for this branch, it's not taken once, and then it's taken. And then for this second branch, it's always taken. Okay, so that dictates the flow of instructions here. Okay, now the other thing, of course, that we're looking at is we're assuming we're using an assume not taken strategy, which means that if the branch is taken, then we have to flush one instruction. Okay. And so our first instance of a taken branch is after is the second branch that's executed. The first branch will be not taken the first time around, and then the second branch is always taken. So let's go look. Okay, here's the first branch. Okay, and then here's the second branch. So the second branch, we'll go ahead and fetch the add, which is the delay slot. We're gonna execute that one unconditionally. And then here I indicate that an instruction was flushed by drawing something in the fetch stage and then crossing it out. Well, that happens. And then we see the BEQ flow. Now, what some people did in their diagrams, which actually to me actually makes a little more sense, is they actually showed the instruction that got flushed. So you could have, and I think it was a store word. You could have a store word here at the next line and then just show that it gets flushed and then show that you would fetch the BQ. In fact, I think in the future I'm going to make my solutions look that way because the diagram really makes sense what's going on. Okay, here it's a little confusing because I just simply cross something out in the fetch and I don't really tell you what it is. Okay, so either way that you do that is acceptable. Uh, so anyway, so we end up with this flush, right? So and there's two flushes because there's two taken branches. So what we do if we go back and look at the code, so we go and we take it, we go to label 1. Well, label 1 puts us back at this branch. Well, now the next thing we do is we take that branch. Okay, so we're going to have the load word, and then we're going to fetch the add, but then we're going to flush it, and then we're going to actually then continue fetching the store word. So we see that in my diagram, although not quite the detail that some of you provided. Um, we have the load word, and then here I have the store word, and then I have this X in cycle 11 that indicates that we flushed an instruction. Again, some of you had the add in here and then showed it being flushed, and I actually liked the way that looked better. So kudos to you if you did it that way. I'll probably gear my solutions that way in the future. Anyway, so most people, a lot of people got the flush because they're like, okay, well, what's the point of this problem? Well, it's looking at the assume not taken strategy and with a branch delay slot. But a lot of folks missed the data hazard that's here. Okay, which it was funny because for problem 7 you just looked at this and then forgot about it. So I tricked you by having a control hazard and a data hazard all in one problem. That's why I like this problem. Okay. All right. So here we have T2, which is being produced by the load word, and then it's being consumed by the branch. Okay. Uh, so what we need, if you recall, if we have data forwarding, okay, which I show we do have full data forwarding and hardware interlocking, then we're going to have to insert a stall there, okay, because it's a load word and there's a load delay there, okay. So we see that here in the diagram. That's how I represent. Notice I hold the branch in decode for an extra cycle, and in this diagram, in my diagram, I've even depicted where the forwarding happens. See, so we got forwarding here. That'll be important when we get to the next part of this problem. Okay, so we're forwarding there. So some people got that and didn't get the flushing. Some people got the flushing but didn't get the delay, load delay. So I don't think anybody really got all of it. If somebody did get it all, um, I apologize for forgetting. Okay. All right. So Part C confused a lot of folks because they weren't exactly sure what that meant with 100% predictors. So I need to spend a little bit of time um, talking about how this is going to work. Okay. Um, so basically, what's going to happen is you're going to have uh, a branch predictor, and it's going to sit in the fetch stage. Okay. And and while you're fetching your branch instruction, you're also going to reference this branch predictor. So when you get to the decode stage, you're going to look and say, oh, you look at the opcode and you say, oh, this is a branch. So then you're going to say, well, let me look and see what the branch predictor says is the direction of the branch. And so then based on that, you're going to then redirect the program counter to start fetching from the branch target. Okay? Um, and so then when the branch gets to the execute stage, you're going to resolve the branch, okay, because that's where all of your data forwarding and everything is happening. So you use the ALU to resolve that branch. And in the simple case of a BEQ, you're going to look at the two register values RS specified by RS and RT, and you're going to say, are they equal? If they are equal, then the branch is taken. If they're not equal, then the branch is not taken. Okay, so that's what I mean by resolving the branch. You do that in the execute stage, okay, for our given pipeline. But then what we do is you look at the branch, how it was resolved, and you also look at how it was predicted. So if it was predicted taken and it resolved as taken, you have nothing to do. No work to do. No flushing. You just continue on. The prediction was correct. You just continue on fetching instructions. Now, if the predictor and the way the branch resolved disagree, now you have to basically flush the instruction in the fetch stage, okay, and you have to then start refetching at the correct path, which if it's supposed to be a taken branch, then you resolve at the branch target. If it's a not taken, you have to then start fetching at PC plus 4, okay? Uh, well, this problem is much simpler to that because we say assume a 100% predictor. So what that means is that when we get to the decode, when the branch gets to the decode stage, we're always going to fetch the next instruction. That fetching is always going to be correct. So no flushing. Okay. So if we go back and look at my diagram in the solutions, okay, see there's no flushes here because it's a 100% correct predictor. Now we still have our data dependencies. Those have to be resolved with stalling and forwarding. Okay, but no flushing. So the previous problem executed in 16 clock cycles, and this one now executes in 14. Okay, so that's how that works. So part D asks for what the speed up is. Well, it's simply 16 over 14. Okay, so execution time old over new execution time, right? So 16 over 14 is the speed up. Okay. All right. Now I really like this problem, by the way, and it might end up on an exam. Actually, there's a really good chance it might end up on your exam. So Hennessy and Patterson in their textbook, they like to talk about moving the branch decision to the decode stage, and they pose this as a very viable solution. So what they're saying is, well, the problem with resolving the branch in the execute stage is you have that extra cycle, okay, that you may have to flush an instruction, right? So if we just go ahead and resolve the branch one cycle earlier, then we don't have that cycle loss, okay, theoretically. So the problem with that is now we have to replicate all of our forwarding logic into the decode stage as well, and we actually have a little bit more forwarding logic because we have an additional stage that we also have to forward from, okay, and now we exacerbate the amount of interlocking that has to happen, okay? Because now we now need our our registers in the decode stage rather than the execute stage like most ALU instructions. Okay, so that's why I created this problem. I don't remember if I created it or if I stole it from the textbook. I think I created it. Anyway, so with this problem, we now look at moving the decision logic to the decode stage, which means we're not going to have any flushing. Okay, but what it does is it makes this particular data hazard between the load word and the BEQ even worse. Okay, and so let's look at that. So again, we won't have any flushing, but now we have this delay. So let me see. I need a blank page here to see the problem. So let's look at our load word, and it goes through the fetch, decode, execute, mem, write back. Okay, and then we have this BEQ, and it goes through fetch, decode, execute, mem, write back. Okay, so the issue is we have this load word, and so let's say we're resolving branches in the execute stage. Okay, the load word is producing its value in the mem stage, and the reason we have to stall is because, well, it would require us to forward backwards. So our arrow would be going backwards in time, and we can't magically do that. Okay, so the way we resolve that is by stalling the BEQ, or you can visualize it as putting a no-op between the load word and the BEQ. I like to just replicate the decode, because really what we're doing is we're holding the BEQ in decode for an extra stage. So now if we do decode, execute, mem, write back, and again we're resolving in the execute stage, now we can forward properly. Our arrow points forward. Okay. Well, now let's say we now move the decision of the resolution of the branch now to the decode stage. Well, if that's the case, then we actually need the data in the decode, which is right here. We produce the value in the memory, and so now we're back to, even with two stalls, or with one stall, we're back to this problem where we're trying to forward backwards in time, and we can't do that. Okay, so what we have to do then is we have to introduce another stall. Okay, and then that now allows us to forward properly. Okay, so that's why understanding the data hazards in addition to the control hazards is very important for this problem, which is why I really love this problem. Okay, and it also brings to light the fallacy of just move the branch resolution earlier in the pipeline. It shows the problems with that. So going back to my solutions, what you're going to see if we go on to the next page is there's no flushing, right? No flushing, okay, because branches are resolved in decode. But notice that for each of these load delays, we had to add an extra delay. Okay, did I do that correctly? Yeah, right here. See, so for each of these data hazards, we have to keep the branch in the decode stage for an extra cycle. Okay. Now going back over here, if we're resolving branches in the decode stage, okay, we now have a delay that has to be inserted even when we have an ALU instruction. So if we have the following instruction sequence, I'm just making stuff up here, okay, and let's go ahead and put a BQ on T and T3, let's just say, in some label here. Okay, so we have a data dependency here, right here, and now if we were resolving branches in the execute stage, we would not have to stall here. But because we're resolving branches in the decode stage, okay, let's look at that in our pipeline diagram. We have fetch, decode, execute, mem, write back, and then we have the BEQ, fetch, decode, execute, mem, write back, and the add produces its value at the end of the execute stage, and the branch needs it now at the beginning of the decode stage, and now we have that scenario where we're trying to forward backwards. So of course what we have to do, even in this case, is we have to have an additional stall. Okay, so now we can of course forward like we're supposed to. So this points out a huge fallacy with moving the resolution of the branch earlier in the pipeline. It's not that easy. We've completely complicated our pipeline by increasing the number of forwarding paths, increasing the amount of interlocking, and all of that. And so that's why I don't like that solution. So the easiest solution is to leave the resolution of the branch in the execute stage and go ahead and add a small branch predictor, which is very simple, requires very little logic, and you saw in previous lectures, even with a simple 2-bit saturating counter, we can get 80 to 90% accuracy. So anyway, that's why I really like this problem, is it points out that fallacy. Part F was really, I need to give you a problem that shows you how to actually calculate the offset for a branch. So in other words, how to turn these branches into machine code. Okay, some of you didn't get that right. Okay, so go back and look at my solutions at how I do that. Okay, some of you forgot that the offset is shifted. That you take the offset and then you left shift by 2, which means when you're calculating your offset, you figure out how far you are from the branch delay slot, and then you figure that out in number of bytes, and then you right shift that by 2. The other way of looking at it is just count your offset based on the number of words you are away from your branch delay slot. The other mistake folks made is they forgot that it is with respect to the branch delay slot. So when you calculate a branch target, you take PC plus 4, and then you figure how far away your label is from PC plus 4. PC plus 4 is your branch delay slot. Okay, so the easy way is to go ahead and count and figure out how many instructions away from the branch delay slot you are. And if you're counting up, then your offset's going to be negative because you're branching backwards. Okay, and if you're counting forward from the delay slot, then your offset's going to be positive. Okay, so well, I can look at this example. Let me cover this real quickly here. Okay, so for this first branch, label 2 from the delay slot, we can see is 1, 2, 3 instructions away. So our offset for this first branch is 3 plus 3. Okay, for the second branch, okay, the label is up here. Okay, so we're pointing to this instruction, and it's from the delay slot, it's 1, 2, 3 instructions away. And because it's backwards, it's negative. Some people forgot that and didn't make their offset negative. So anyway, the second branch has an offset of -3. Okay. All right. I really like this last one, and this of course is my own making. So that's probably why I really like it. And what it does is it points out some of the design decisions that the original MIPS designers were faced with. So some pipelines go ahead and integrate the multiplier into the ALU, and really what that ends up doing is it ends up destroying your clock cycle time, okay, or complicating the logic. So this problem kind of shows that. So the first part of the problem basically says that the multiplier adds 300 picoseconds to the latency. If you've already looked at my homework solutions, you'll see that I screwed up on that. Okay, and when I upload this new set, you'll see where I had to correct myself. I made the problem, but I also, when I go to do the solutions, I read it wrong, and I said that I read it as it made the ALU latency 300 picoseconds, not that it added 300. So anyway, you'll see that I had to correct that. But anyway, so it adds 300 picoseconds, which means that the ALU that used to take 100 picoseconds now takes 400 picoseconds. Okay, so you take 660 and you add 300 picoseconds to that, and you get 960. So for the single cycle, 1 over 960 picoseconds is your clock rate. Okay, so it tanks the clock rate. And then I ask you to calculate the speed up achieved by adding the multiplier. And this is where some people just said, this is an out. I don't have to calculate speed up because it actually slowed down. No, 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 no. I want you to calculate speed up and find that the speed up is a fractional component, which then indicates that it was a slowdown. Okay, so the reason, of course, that it's a slowdown is because so your clock rate decreases, but by a much larger percentage than the amount of instructions that you save. Okay, so the whole point of adding a multiplier is that in this particular example, which is just made up numbers, somewhat made to represent real life, 20% of your execution of your instructions that are executed can be rolled up into a multiply. So what that means is that if your particular data path does not have a hardware multiplier, okay, that when you need to do multiplications, that has to be emulated in software. Okay, so that required 20% of this particular instruction stream was emulating multiplies. So as soon as you include a hardware multiplier now in your design, then those 20% of your instructions don't even exist anymore. So that's where the savings comes from. Okay, so you just decrease your instruction count by 20%. And this is typical. You add a multiplier, that is where you save. Now, you might save a lot more. Like in public key encryption, you spend 90% of your time doing multiply. So you're going to save a lot more if you're doing a lot of multiplies by adding a multiplier. Okay, but where you lose is the fact that your clock rate tanked. Okay, and so part B told you, identified just how much it tanked, which if we go back and look at the solutions, let's see. Let's go back here. Okay. Oh, well, no. I'm getting ahead of myself. Part B is still including the... I'm sorry. I'm getting ahead of myself. Part B is still including the savings for instructions, reducing the instruction count. So you have the slowdown that's due to your increased clock rate, but then you have a slight speed up due to the 20% reduction in instructions. So I'm basically asking you to calculate that. Now again, my solutions are incorrect, so I had to fix that, but basically you're going to take you calculate the ratio of your clock rate, okay, which because I screwed up, this is actually going to be slower. This is going to be a higher ratio, so it's 1.45, I believe. Let me look at my 1.45. Let's see. Yeah. Homework. Yeah, whatever. My homeworks are all jumbled, but I'll upload the corrected solution. So let's just say it's 1.45x. Then this will be 0.8 times 1.45. Okay, and I have my homework solutions on the desk here, and they all got shuffled. So now I'm lost. I have no idea where. Oh, here we go. Okay. Yep, 1.45. Okay. So then this becomes, let me look at my solutions, this becomes 1.6, a slowdown of 1.6, which then our speed up is 1 over 1.6, which is then 0.862. Okay? So that's our speed up, and because it's a fractional component, we know that we're not actually speeding up then. Okay? All right. Okay, now, in keeping with the pipeline theme, we decide to. Okay. You know what? I'm gonna take a minute and make sure that everything's good with this project because I do not trust this thing. Okay, just as I had suspected, the thing crashed right after I checked it. But luckily, I went in and looked at the log files and figured out where it was storing those magical temporary files. I was able to load them on. Nothing in Windows opened them. I put them onto my Linux machine, found a tool that would open them, and it stored the audio in a separate WAV file and the video in an MKV file, and I was able to merge them with the Linux tools and then re-import them into this stupid active presenter. This is what the faculty recommend us using for recording lectures, so lovely. All right, I'm not very happy with this tool, but I'm going to try to complete this, what's supposed to be just an hour and 15 minutes, and it's burned a good portion of my day just trying to get this homework solutions done. Okay, enough venting. Sorry about that. All right, so we're talking about number 9 and how it works with pipelining, and I don't want to spend too much more time with this. I'm kind of tired of this homework solutions. Basically what happens is you're going to, your ALU now has an additional 300 picoseconds of time. So if you remember the last, if you go back to number, number 8, okay, the solutions to number 8. Okay, this is, those are not my solutions. Okay. In the execute stage, we had a 115 picosecond delay through that stage. Well, now if we add 300 picoseconds, that now bumps it up to 415 picoseconds. So you can calculate the slowdown based on that. So your clock rate again is 1 over 415 picoseconds. It's a hell of a lot slower than 1 over 200. So we see a slowdown even with a reduction in 20% of the dynamic instructions that are executed. Okay. So the final part says, well, now in keeping with the pipelining theme, we're going to do what MIPS did, and that's pull the multiplier out of the pipeline, and then we're going to further pipeline it. So we're going to break it up into 2 stages, each stage taking 150 picoseconds. Okay? So now what's going to happen is each stage takes 115 picoseconds for the multiplier. It's now pulled out of the main pipeline, which means now our critical path is again through the fetch and memory stage, which are each 200 picoseconds. So that means we can run this pipeline now at full speed, and then part F is saying in an idealized situation, assume that pipelining the multiplier and pulling it outside of the pipeline adds no additional data hazards, and calculate the speed up that you get from that. And so then that's basically 1 over 0.8, where 0.8 was the number of instructions that you have to run now with the multiplier. Okay. Before I totally go insane, I'm going to go ahead and finish this, and then I'm going to upgrade this darn tool. I'm thinking maybe that's the reason it's getting mad and crashing. And then I'm going to attempt to record the actual lecture. Okay, thank you for tuning in, and hopefully this was helpful. Please do post questions to the discussion board or email me with any questions you might have.